Treatment design is a constrained system. Design variables are limited by surface capability, formation behavior. Now define design variables: acidizing, fluid, rate, volume, fracturing, fluid, proppant, geometry. These variables define performance. Now define constraint systems: surface system, subsurface system. Now surface system constraints: maximum injection rate, limited by pump capacity; maximum surface pressure, limited by equipment rating; fluid preparation, limited by blender and storage capacity; operational limits, temperature handling, safety distance, logistics. Now subsurface constraints: breakdown pressure, minimum pressure required for fracture initiation; closure stress, defines proppant strength requirement; fracture gradient, defines upper pressure limit; temperature, controls fluid stability; fluid compatibility, controls chemical reaction and precipitation risk; natural barriers, control fracture height containment. Now define design condition. All variables must satisfy surface limits and subsurface limits at the same time. Now define failure. If design exceeds surface limits, execution fails. If design exceeds subsurface limits, formation response deviates. Now final statement. Design is valid only if it is achievable within both constraint systems. Treatment design is bounded by two systems: surface system, subsurface system. Now define surface constraints. Pump capacity defines maximum achievable rate as a function of treating pressure. As pressure increases, maximum achievable rate decreases. This defines the rate pressure operating envelope. Now surface pressure limit. Equipment is rated for maximum allowable pressure. Includes wellhead, treating iron, manifold. If surface pressure exceeds rating, mechanical failure occurs. Now define fluid handling constraint. Blender capacity limits, maximum proppant concentration, maximum slurry rate, storage limits, total available treatment volume. Now define subsurface constraints. Breakdown pressure defines minimum pressure required to initiate a fracture. If bottom hole pressure is below this value, fracture does not form. Now closure stress defines load acting on proppant after pumping. Proppant strength must exceed closure stress. Otherwise, grain crushing. Fines generation, conductivity loss. Now fracture gradient defines upper pressure limit for matrix treatments. If exceeded, unintended fracturing occurs. Now temperature controls fluid viscosity stability. High temperature reduces viscosity over time. Transport capacity decreases during treatment. Now fluid compatibility. Chemical interaction may produce precipitation, clay swelling, asphaltene deposition. These reduce permeability near the wellbore. Now define failure condition. If required rate exceeds pump capacity, treatment cannot be executed. If required pressure exceeds equipment limit, operation becomes unsafe. If fluid is unstable at reservoir temperature, transport fails. If proppant strength is insufficient, conductivity fails. If pressure exceeds fracture control, geometry becomes uncontrolled. Now conclusion. All constraints must be satisfied simultaneously. Otherwise, design fails regardless of optimization quality. Injection rate is limited by pump power. Pump output is defined by maximum horsepower. Now define relationship. Rate multiplied by pressure is constant for a given pump system. As treating pressure increases, maximum achievable rate decreases. This defines the operating envelope. Now define treating pressure. Surface pressure plus hydrostatic head minus friction losses gives bottom hole pressure. Surface system must withstand maximum surface treating pressure. Equipment rating defines upper limit. Now define constraint condition. Required rate must be achievable at required treating pressure. If required rate exceeds pump capability, flow cannot be sustained. Now define failure. If rate is forced above capability, pressure drops. Fracture does not propagate as designed. If pressure exceeds equipment rating, mechanical failure occurs. Now define friction effect. Higher rate increases friction losses. Higher friction increases surface pressure. This reduces available pressure margin. Now define design implication. Rate and pressure cannot be selected independently. They are coupled through pump capacity. Final condition. Design rate must lie within pump rate pressure envelope and equipment pressure limit. Formation response is controlled by pressure limits. Define 4 constraints. Breakdown pressure, closure stress, fracture gradient, stress contrast. Now define each. Breakdown pressure. Minimum bottom hole pressure required to initiate a fracture. If bottom hole pressure is below this level, no fracture forms. Injection remains in matrix flow. Now closure stress. Normal stress acting on fracture faces. After pumping stops. Controls fracture closure. Defines minimum proppant strength requirement. If proppant strength is lower, grain crushing occurs. Conductivity is reduced. Now fracture gradient. Defines pressure threshold. For fracture propagation. Below this level, flow remains in matrix. Above this level, fracture growth occurs. For matrix treatments, pressure must remain below this value. For fracturing, pressure must exceed this value. Now stress contrast. Difference in stress between target layer and bounding layers. Controls vertical fracture growth. High contrast. Fracture height is contained. Low contrast. Fracture grows beyond target interval. Now define constraint interaction. Bottom hole pressure must satisfy greater than breakdown pressure and within equipment pressure limits. Fracture propagation must remain within vertical boundaries. Now define failure. If breakdown pressure is not reached, no fracture is created. If pressure exceeds intended limits, fracture grows out of zone. If closure stress is underestimated, proppant fails after treatment. Now final condition. Formation pressure constraints define whether fracture initiates, how fracture propagates, and whether fracture remains effective after closure. Treatment operation is bounded by a combined limit. Surface capability. Formation response. Now define interaction. Injection system provides rate. Surface pressure. Formation requires minimum pressure for initiation. Sufficient pressure for propagation. Now define operating condition. Injection must satisfy both required rate, required bottom hole pressure. At the same time, now define coupling. Increasing injection rate increases friction losses. Increases surface pressure requirement. At constant pump power, increased pressure reduces achievable rate. Now define operating window. Lower boundary. Minimum pressure required for fracture initiation. Upper boundary. Maximum allowable surface pressure. Within these limits, treatment can be executed. Outside these limits, operation fails. Now define limiting cases. Case 1. Required pressure exceeds equipment limit. Fracture cannot be initiated or sustained. Case 2. Required rate exceeds pump capacity. Target geometry cannot be achieved. Case 3. Friction losses consume available pressure margin. Effective bottom hole pressure drops. Fracture propagation is reduced. Now define design condition. Selected rate and pressure must lie inside pump capability envelope and formation requirement range. Now final rule. Design variables must be selected within the intersection of surface limits and subsurface requirements. Case is defined by 3 constraints: high closure stress, limited surface pressure, moderate permeability. Now define implications. High closure stress. Proppant must resist high compressive load. Low strength proppant is not acceptable. Now limited surface pressure. Maximum achievable bottom hole pressure is constrained. Injection rate cannot be increased beyond limit. Now moderate permeability. Conductivity is limiting factor. Fracture width is more important than length. Now define required adjustments. Injection rate. Reduce rate to stay within pressure limit. Recalculate fracture geometry at reduced rate. Longer pumping time may be required. Now proppant selection. Select high-strength proppant. Material must withstand closure stress over production life. Now fluid system. Select fluid with lower leak-off. Increase fluid efficiency. Recalculate pad volume for constrained rate. Now define result. Fracture growth is controlled. Conductivity is maintained. Treatment is executed within limits. Now define failure conditions. Case 1. Surface pressure exceeds equipment rating. Mechanical failure occurs. Operation stops immediately. Now Case 2. Fracture grows outside target interval. Stress containment fails. Non-productive zones are connected. Now Case 3. Fluid is incompatible with formation. Precipitation occurs. Permeability is reduced. Now final condition. Exceeding constraints leads to treatment failure, safety risk, production loss. Design is a constrained optimization problem, not a maximization problem. Objective is maximum achievable performance within system limits. Now define condition. A design is valid only if it can be executed and it remains within formation limits. Now define implication. Increasing size without feasibility does not improve performance. Now define comparison. Achievable design. Executed as planned. Maintains integrity. Delivers controlled result. Unachievable design. Cannot be pumped. Or fails during execution. Now define decision check. Step 1. Equipment check. Required rate must be achievable. At expected treating pressure. Surface system must withstand maximum pressure. Now Step 2. Formation check. Breakdown pressure must be reachable. Selected proppant must withstand closure stress. Now Step 3. Compatibility check. Fluid must remain stable throughout treatment. No adverse reactions with formation minerals. Now define output. If any condition is not satisfied, design must be modified. Execution is not permitted. Now final rule. Design that fails constraint check must not be pumped. 1. Always design inside the operating window. Define minimum required pressure, maximum allowable pressure, maximum achievable rate. Never start with target geometry. Start with feasible limits. 2. Verify pump capability before finalizing rate. Check. Required rate at required pressure. If not achievable, reduce rate and redesign geometry. Do not assume rate is available. 3. Match proppant to closure stress. Use measured closure stress, not estimated, if strength is insufficient. Conductivity will fail after pumping. No correction is possible later. 4. Design fluid for actual downhole conditions. Check temperature stability over full pumping time. Check compatibility with formation. If fluid degrades, transport fails during the job. 5. Recalculate everything when one constraint changes. Rate change effects. Length. Width. Transport. Fluid change effects. Transport. Leak-off. Geometry. Never adjust one variable in isolation. 6. Do not exceed system limits. Exceed equipment limits. Job stops. Exceed formation limits. Fracture becomes uncontrolled. Both lead to failure. 7. Final rule. A smaller treatment that is executed correctly outperforms a larger design that cannot be delivered. Design is constrained, not optional. Surface limits define. Maximum rate. Maximum pressure. Formation limits define. Fracture behavior. Proppant requirement. Fluid stability. Rate and pressure are coupled. You cannot choose them independently. Geometry must be designed within achievable limits, not target values. If one constraint is violated, the system fails. Final rule. Achievable design is the only valid design.